Osmotic pressure, theory, measurement, and biological significance. Osmotic pressure is a fundamental thermodynamic property arising from the phenomenon of osmosis, in which solvent molecules spontaneously migrate across a semi-permeable membrane from a region of lower solute concentration to one of higher solute concentration. This process continues until thermodynamic equilibrium is achieved or until an equal pressure is applied to counterbalance the solvent flux. The magnitude of this opposing pressure defines the osmotic pressure, pi, a key parameter governing both natural and engineered systems. Osmosis plays a central role in biological function, including cellular fluid balance, nutrient transport, and water uptake in plants. In animal cells, osmotic gradients regulate membrane tension and volume homeostasis, while in plants, they drive turgor pressure essential for structural integrity. Technologically, osmotic pressure underpins applications such as desalination, controlled drug delivery, and membrane separations. Its quantitative description has therefore been the subject of extensive theoretical and experimental investigation for over a century. The earliest quantitative framework for osmotic pressure was established through the pioneering work of Jacobus Henricus van 't Hoff, who demonstrated that dilute solutions obey an equation formally analogous to the ideal gas law, expressed as pi equals RTC, where R is the universal gas constant, T is the absolute temperature, and C is the solute concentration. This relationship highlights the colligative nature of osmotic pressure, depending solely on the number of solute particles rather than their chemical identity. Building upon this, Morse introduced a modified expression based on molality, improving applicability to slightly more concentrated solutions. Despite their foundational importance, both equations assume ideality and neglect intermolecular interactions, leading to deviations even at relatively low concentrations for macromolecular or strongly interacting solutes such as proteins and polymers. To address non-ideal behavior, more sophisticated models have been developed. The virial expansion approach extends the van 't Hoff framework by incorporating solute-solute interactions through concentration-dependent coefficients, enabling accurate descriptions of dilute but non-ideal systems. Higher-order virial coefficients account for multi-body interactions and have proven particularly useful in characterizing polymer and protein solutions. For concentrated systems, thermodynamic models based on solvent activity, such as the Van Laar equation and free solvent models, provide improved accuracy by explicitly incorporating solute-solvent interactions and deviations from ideal mixing. These approaches relate osmotic pressure to the chemical potential of the solvent and its activity, thereby capturing the complex behavior of real solutions. An alternative conceptual framework is provided by the vapor pressure theory, which interprets osmotic pressure as the pressure required to equalize the vapor pressure of a solution with that of the pure solvent. This perspective emphasizes the role of solvent chemical potential and provides a thermodynamic basis consistent with phase equilibrium principles. It also offers a physically intuitive description of how solute addition lowers solvent vapor pressure, thereby generating osmotic effects. Despite these advances, classical and semi-empirical models often require experimental calibration and are limited in predictive capability across wide concentration ranges. To overcome these limitations, mechanistic approaches based on irreversible thermodynamics and diffusion theory have been proposed. In such models, osmosis is treated as the net result of coupled or uncoupled diffusion fluxes of both solute and solvent across a membrane. A notable example is the theory proposed by Granick and co-workers, which models osmotic pressure as arising from opposing solution fluxes described by generalized Fickian diffusion. This framework introduces effective diffusion coefficients for the solution as a whole and accounts for membrane permeability, solute size, and transport asymmetry. Importantly, it does not rely on adjustable parameters and is applicable beyond the dilute regime, offering a more predictive description of osmotic behavior. Experimental validation of osmotic pressure theories is commonly performed using membrane osmometry. Studies on aqueous sucrose solutions over a wide concentration range have demonstrated that mechanistic models can closely reproduce measured osmotic pressures, although slight systematic deviations are often observed at higher concentrations. These discrepancies are generally attributed to concentration-dependent changes in solution properties and to complex interactions between solute molecules and membrane pores. Similar trends have been reported for other solutes, including glucose, glycerol, and ethylene glycol, where experimental data align well with theoretical predictions but exhibit minor deviations that highlight the need for further refinement of transport models. Beyond physiochemical theory, osmotic pressure has profound biological implications. Cells are highly sensitive to osmotic conditions, which are commonly classified as isotonic, hypertonic, or hypertonic relative to intracellular environments. In hypertonic media, cells swell due to water influx and may undergo lysis, as observed in red blood cell hemolysis when extracellular osmolarity decreases significantly. Conversely, hypertonic conditions lead to cell shrinkage and impaired function. Maintenance of near isotonic conditions is therefore essential for physiological stability, with deviations contributing to pathological states such as hyponatremia, hyperglycemia, and kidney dysfunction. Osmotic pressure also plays a critical role in dynamic cellular processes, including cell division, differentiation, and membrane organization. For instance, osmotic gradients drive the morphological changes required for mitotic rounding, a process essential for proper tissue development. In medical practice, osmotic principles are exploited in therapies such as dialysis, where semi-permeable membranes facilitate the removal of metabolic waste, and in the use of osmotic agents to reduce intracranial pressure in cases of cerebral edema. In summary, osmotic pressure represents a cornerstone concept bridging thermodynamics, transport phenomena, and biological function. While classical theories such as the Van, T. Hoff and Morse equations provide a useful foundation, their limitations in non-ideal and concentrated systems have prompted the development of advanced models incorporating molecular interactions and transport mechanisms. Recent mechanistic approaches offer promising predictive capabilities, yet challenges remain in achieving universal applicability across diverse systems. Continued integration of theoretical, experimental, and computational methods is essential for advancing the understanding of osmotic pressure and its role in both natural and engineered processes.